TCM really shines when you use it with the newer technologies like the Arkema nanotechnology. The commercial name is Blockbuilder, but basically what you do with a nanotechnology is you get a complete control over the exotherm process because you're handing over the reactivity to your temperature-controlled mold system. And that allows you to gradually and evenly cure a part regardless of configuration, regardless of number of plies, and regardless of thickness. So there's a few components, and what we have here are just the lab molds or the training molds. We have a fluid that runs fairly close to the mold surface, and that is controlled by a temperature controller. And we have pumps, we have circulation. Again, that's the idea that we can maintain the surface temperature of the mold at any set temperature. Does it have to be flat? Absolutely not. Fiberglass molds have the advantage that they can be any shape and any size. And one controller can control a fairly large zone. When I say fairly large zone, biggest tables we have running right now are 20 by 60 feet. That's feet, 20 feet by 60 feet. And that runs on a single unit. But of course, you can zone off any mold in sections that are logical and that you'd like to subdivide either because of the laminate or because of production factors, or in the case of a flat table, because of the practicality of not having to heat the entire table or cool the entire table. That's in a nutshell, the technology. The advantage of this system compared to other systems that are out there is that it really is stable. So you can dictate what your ramp rate is. You can dictate how quickly a laminate is allowed to exotherm. You can draw a tremendous amount of heat out of the laminate, or you can add a tremendous amount of heat if that is necessary for a certain process. And you can do it fairly quickly. This table works as well for pre-pregs, because here you got a perfect surface to make your pre-pregs on. And again, since any mold shape can be made into a TCM mold, you can pre-preg with this table. But what I see as a major advantage is that you're not limited to one technology. You're not building the mold for pre-preg or for resin infusion. It's a multifunctional mold. So that means that even if your application is only temperature controlled at room temperature, well, we're not talking room temperature on a good day and a bad day. We're really talking temperature control at the mold level. So regardless of what the shop circumstances are, you can maintain temperature control at the mold level. So you can make perfect laminates. So you got vacuum infusion, with nanotechnology, you got high temperature infusion, for instance with epoxy resins in wind blades. While your mold may be more expensive than your normal molds without temperature control, this is your investment. If you have a regular mold, you're fighting temperature every day. Temperature up, temperature down, cool day, hot day. By bringing the temperature control to the mold, your requirements on your environment are a lot less. You don't need ovens, you don't need curing ovens. You don't need a controlled environment. You can really dial down the temperature during manufacturing and during layups to a comfortable level for the employees, even if at the mold you maintain a higher temperature. So you can work very comfortably. What's the outcome of that? Well, money. The savings are significant. If you can maintain your shop temperature way down and your productivity up, then right there you start realizing tremendous savings. But there's another factor to this. You don't have to use up your resin after you've initiated it, after you catalyzed it, as we usually say in the trade. You don't have to use it all up. That batch can be stable up to a week, which means that even the resin that has been mixed up for one part, whatever you have left over can be used for another part without having to worry that it's going to go off on you, without worrying that it's going to gel on you. Also, you don't have a time limit. It doesn't matter that your batch was mixed a few hours before that, you're not going to lose that material. It will remain stable as long as you maintain it within that temperature bracket before you let the decapping happen. You're only starting to engage that decapping process after you've finished your infusion, which means that your infusion time is, I wouldn't call it unlimited, because that would be a hard claim to make, but it's definitely giving you days of time, and the moment you finished your infusion, you're not dealing with leftover reactivity that you have to wait for it to complete. You just bring up the temperature and start the cure. So we've really split out, from a process point of view, we split out the active phase of preparation, infusion, versus the cure. So it's cure on demand, and there again, the gains from a process point of view and from just a pure money point of view are significant. This is an absolutely perfect system, because you have a lot less setup time, you have a lot less prepped material, batches of material sitting around. So it's, even in closed molding, it's one of the cleanest processes you can ever see. And of course, if you go in a production process where you have metered mixing, you have a completely, I would say, automated process. The cure on demand is really the big difference here. It changes so many parameters in what's happening in the shop and how it's happening, because you don't have to do all that prep work, and you don't have to kind of rush into getting a part completed. You have all the time in the world. In very difficult infusions where they're actually going to a recirculation, you know, where you put resin through, you can do that. You can do that, and the resin that comes back out can be used again. So it's really a system that has a tremendous amount of flexibility. Now, talking about strength, one of the surprising things, because when we started working with this, we weren't really in the first place after mechanical properties. We were trying to get the process under control for large composites, thick composites, and high fiber loads. So that was really what we were after. And we would have been very happy to just match the properties that we were getting. So we were very surprised when we started cutting pieces up that we were having a really hard time. You wouldn't think that a vinyl ester glass part would be hard to cut. Well, I can tell you, when you have a part that's made with TCM and with you know, the controlled radical polymerization, or CRP, in that case, we were surprised how tough these parts were to cut. And then consequently, we did some testing on that. The first thing we did was short beam shear strength, and the numbers on the short beam shear strength were systematically up to 25–30% higher than we could have with the identical laminate done in the usual fashion. So we were surprised about that, and we're now realizing that we may actually have another advantage. So we already have the fact that we have unlimited processing, much better parameters in that. We also have the possibility on making thick laminates in a single shot, so we don't have weak areas in the laminate where you have secondary bonding. But we also have really nice three-dimensional even cross-linking. Because of the gradual controlled cross-linking that we see, we have a lot less stress in the laminate, and we have higher mechanical properties.